Good evening to you, everybody. We are going to discuss today uh, a current lively topic that is decarbonization and path to net zero energy buildings. And we are all discussing about energy, how energy we are going to save, sustainability, and then green buildings. What are these green buildings? All that we'll discuss in this little talk. These are the contents that we are going to go through today: decarbonization, net zero energy buildings, sustainability, net zero energy concept, greenhouse gases, case studies of net zero carbon buildings, building services engineers' role that has a certain part that all the building service engineers supposed to do. Then use of building management systems to conserve energy. So these are our contents today. Decarbonization. Now this is, this is a new word, but then it is the same thing that we are talking about. Climate change mitigation is decarbonization. This is action to limit climate change. How to reduce carbon emissions, and also going towards removing carbon from Earth, that kind of a scenario. Now, recent rising global temperature that we have seen, what we have seen here so far, climate change, sometimes one part of the Earth world facing huge drought, where the other side a massive rain and earth slips. All that is due to the global warming. So our ultimate aim with regard to sustainability and going for green buildings, ultimate aim is to reduce global warming. Now, it is possible to remove carbon dioxide from atmosphere. New techniques are there. This can be done passive ways. It can be done by enlarging forests, new forests, resorting to wetlands, and using other natural and technical processes. So, the other term is net zero energy buildings. Net zero energy buildings are designed first to significantly reduce energy consumption. First aim there in the net zero buildings to reduce energy consumption of the building at least to 50% of the current value, and then to meet remaining loads with renewable sources. Ideally, those renewable sources are located on site. These buildings are usually connected to utility grid to receive energy whenever renewable energy production is insufficient to meet the required loads, and to return energy to the grid when renewable energy production exceeds the loads. Now, on your right, you have a picture of the new ASHRAE global headquarters. I will just mention what is ASHRAE because we use ASHRAE standards. ASHRAE is American Society of Heating, Refrigerating, and Air Conditioning Engineers. That is the world's largest engineering institution with 50,000 members. And they are in 190 countries, and Sri Lanka, we have our Sri Lankan chapter as well. Now, ASHRAE headquarters was in Atlanta. Of course, this new one was also in Atlanta, but that was a green building. they have moved to a new building that is net zero energy building. So that is a good example. And also ASHRAE has now newly published a standard, that is ASHRAE standard 228, 2023, last year. Standard method of evaluating net zero energy and zero net carbon building performance. So now we have a way to find whether the building or group of buildings meets the definition of zero energy, zero net energy. Then we'll have to just quickly discuss what is a green building. Now, green building is not a green with foliage and trees and green color. No. Green building is a normal building converted to a green building with minimal energy consumption, minimal carbon emissions, minimal water usage. Likewise, minimal impact on site ecosystems, maximum quality of indoor environment. So that kind of a building we call a green building. And green building certifications all over the world, the leading green building certification authority is Leeds from US. Sri Lanka, we have Green Building Council of our own Sri Lankan Green Building Council that certify green buildings. Then we'll have to touch what is sustainability before we embark on net zero thing. What is sustainability? It is everywhere we hear this. Stale subject also now. Now, relation to sustainability is given in ASHRAE. So ASHRAE defines sustainability as providing for the needs of the present without detracting from the ability to fulfill the needs of the future. Others have defined sustainability as the concept of maximizing the effectiveness of resources use while minimizing the impact of the use on environment. That is one way, but it is save for future. Now, factors impacting sustainability are population growth and migration. If you take entire world, food supply, this is control and improving standards. Those are problems and it impacting sustainability. Energy resources availability is not readily available, so those are impacting. Material resource availability and management, fresh water supply for all the people, both potable and non-potable. Effective and efficient usage practices for energy, resources, and water. Air and water pollution. Solid and liquid waste disposal. And land use. All these factors will impact sustainability. Now, is there any myth of net zero carbon buildings? Is it a myth or is it practically achievable? So it is evident that approaching net zero carbon buildings is a difficult task. However, of course, it is achievable. How? Reduce embodied carbon of the building by selecting appropriate materials with low embodied carbon and effective transportation. We'll see what is embodied carbon. Reduce operational carbon of the building by reducing heat gains, utilizing energy efficient equipment and efficient operation. Overall, reduce energy consumption. Thirdly, offset fossil fuel energy by renewable energy sources, similar to solar photovoltaic or wind power or ground source heat pumps and energy, and especially storage devices. Actually, this is achievable. Now, embodied carbon and operational carbon. What is this? Net zero carbon approach needs to address reduction of both embodied carbon and operational carbon in a building. Embodied carbon. What do you mean? Is it carbon is embodied in the building? No. Whatever we do to produce building materials, construction, transportation, those processes eventually emit carbon dioxide to atmosphere. Now that is taken as embodied carbon of a product. So in simple words, the amount of carbon emitted during the making of a building is that is where embodied carbon you find. It includes extraction of raw materials, manufacture and refinement of materials, transportation, the building phase of the product and structure, and the deconstruction. Mind you, at the end of the lifetime, that building has to be removed. Disposal of materials at the end of the life, all that. On your right, you can see here. On your right, you can see embodied carbon in bricks used in construction project. Firstly, energy to dig the raw materials out of the ground. Now that involves some percentage of carbon emissions to atmosphere. Energy to shape clay, sand and water in blocks. Energy to heat and shape blocks and turn them into bricks. Energy to transport a bricks to site. Inside the site, energy to use bricks on site. Finally, at the end of the lifetime, energy use if bricks are wasted and loss of resources, if landfilled, that kind of a thing. So anyway, these are all connected to embodied carbon. Operation carbon, on the other hand, already there are 2-3 questions. I will take this up a little later. Right, operation carbon, that refers to all the energy used in managing and maintaining the function of a building. So energy that we use, ultimately we emit carbon dioxide to atmosphere. Not all the energy, especially fossil fuel, but if you use renewable energy, we don't. It includes heating, cooling, lighting, and any other power usage need to run a building. So operational carbon currently accounts to 28% of global greenhouse gases. If I go back, I forgot to tell you, a embodied carbon at present Embodied carbon only accounts for 11% of global greenhouse gases, only 11%, whereas operational carbon 28%. Significant values we'll have to reduce. So why we are all doing this? Our main target is to stop global warming. Otherwise, global warming increases, there will be bushfires, a temperature will increase, a water level goes up, island nations will disappear like Sri Lanka, and that will be end of our life in Earth. So we'll have to quickly start stopping global warming further. Now there are targets, 1.5 degrees C target. We'll discuss this later. Net zero energy concept. As per ASHRAE, there are a number of different terms commonly used to describe buildings that achieve balance between energy consumption and energy production. There are zero energy, zero net energy, net zero energy, whatever it is. Action taken to reduce emissions from operational embodied carbon with residual emissions compensated via compensation activities in the transitions to net zero emissions. Now, definition of net zero energy building. An energy efficient building where on a source energy basis, the actual delivered energy is less than or equal to on-site renewable energy. So if a building on-site renewable energy is equal to actual delivered energy, then it is a net zero energy building. What comes to our mind quickly? Let's see, we are going to have solar PV in a building. Now, how much we are going to use solar panels in a building? To cover up entire energy you use should be given by solar PV. Okay, so let's say we achieve that. But during night, what are you going to do? During night, or no solar, no sunlight, no solar energy. So we'll have to save. We'll have to use batteries to store energy. So that is another part in net zero energy building. But to do this, firstly, you'll have to reduce your energy consumption of your building to 50% level. Now, ASHRAE has a energy saving standards 30% standard and 50%. These are the targets. Another concept is carbon capture. Now, carbon in the atmosphere can be captured and stored in the ground. Very innovative idea. Now it is being developed. What you can see in this picture is collecting carbon from the atmosphere. Carbon capture and storage is a process in which relatively pure stream of carbon dioxide from industrial sources is separated, treated, and transported to long-term storage location. Right, so that is one way of reducing carbon and reducing global warming. But when we talk about global warming, it is essential for us to know greenhouse gases. What are these greenhouse gases? GHGs. Greenhouse effect occurs when greenhouse gases in a planet's atmosphere trap some of the heat radiated from the planet's surface rising its temperature. You know, this phenomenon happens during day, the normal phenomenon. It happens during day, sun heat up earth. But during night, energy re-radiated back to the atmosphere. But this process will hamper if you have clouds. Then what will happen? The re-radiated energy comes back to earth again and again, and raising the earth's temperature. We can, I mean, we have practiced that. If there's a cloud cover, we feel slightly warm. Now, this is something else. Our greenhouse gases in the atmosphere, now that will have an effect. That redirect the heat back to earth, raising the temperature. So these are called greenhouse effect. Greenhouse gases, constituents, they are constituent of the atmosphere which causes the greenhouse effect. What are those? Water vapor, carbon dioxide, nitrous oxide, methane, ozone are the primary GHGs in Earth's atmosphere. Now, this global warming is taken as a global warming potential. Now, what happened was, initially you could remember, people were using carbon CFC gases, chlorofluorocarbon gases. Initially, our refrigeration systems are used natural gases, carbon dioxide, methane, sulfur dioxide, chlorine, that kind of ammonia, that kind of a thing. But in 1920s, they found very safe refrigerants. Those were CFC. But unfortunately, at a later stage, 1970s, they found these chlorofluorocarbon refrigerant, especially their chlorine is attacking a atmospheric ozone and disturbing the ozone layer. As a consequence, ultraviolet rays hitting Earth, that will keep global warming rising. So, some of the refrigerants where the global warming potential is high is now face down, going to face down and eliminate from Earth. Now, those refrigerants are not CFC already. CFC is already banned and removed. Of course, we are using them sometimes, but this is not in production. The other gas called HFC gas, hydrofluorocarbons. Very common gas is refrigerant is 134A. Our all in automobiles, 134A. Now, 134A gas replaced R12. That is, the 400 series is a blend, zeotropic blends. One common gas is 407C. It is a replacement gas for R22, drop-in replacement. On the other hand, very new refrigerant 410A for air conditioners. Now that is also being now questioned and try to remove. So HFCs are going to be removed. The reason, these chemicals do not deplete atmospheric ozone layer, but some of them have high global warming potential. So that is the problem. So Montreal Protocol, which removed CFC, there's a little amendment to protocol called Kigali Amendment. In France, they did. And that is to remove hydrofluorocarbons. And these are the schedule how they remove. Sri Lanka 2018 ratified to this amendment. So we are now moving 2024. We are trying to curtail imports in these few years. So global warming. What is global warming? You know what is global warming? The repercussions and consequences are, but you can see on your right, massive bushfires and ice caps are melting. So water levels are rising. So Kigali Amendment is what it says. To reduce the global temperature rise below 2 degrees C, they are going to keep 1.5 degrees C pathways in this amendment. We'll take case studies of zero carbon buildings. Now, zero carbon buildings, what we discussed, first we'll have to reduce energy consumption to 50%. That is annual energy consumption. You can yourself, you can find your annual energy consumption of your house. If it is 300 kilowatt hours, you can find annual kilowatt hours. And you can use, we are discussing that later, how to calculate the carbon, equivalent carbon of these emissions. And that is the carbon footprint of your building. So first step towards net zero buildings to reduce energy consumption by 50%. Then apply renewable sources, renewable energy sources, and energy storage. Case study 1, Bavar Residence, Chennai, courtesy of Midori Architects. Bavar House in Chennai is a pioneering residential building that sets itself apart with its zero energy requirements and passive design strategies. A lot of passive design strategies they have used for ventilation, natural light. This has 3 stories. We'll go through this. The project area is 330 square meters. Energy performance index 0.77. That is annual kilowatt hours divided by total area per year. Annual energy consumption per year divided by total area, excluding the car parks. Right, ventilation design. Utilizing aerodynamic foams. Now, the floor plates where this floor plate you can see that is being rotated, not X and Y. The horizontal and vertical axis has slightly rotated to invite wind currents. The floor plates were rotated by 12 degrees clockwise to enhance the Venturi effect in the central atrium, while transitional spaces such as terraces and lobbies were designed to allow indirect sunlight to windows. The design, all these design elements ensure a constant airflow of 0.625 meters per second, even with outdoor wind velocities as low as 0.7 meters per second. That is quite interesting. Daylight. Now, they have used passive strategies. The residence has been deliberately designed with a central atrium, ensuring ample daylight in all regularly occupied areas. To optimize the natural light while minimizing glare, windows are strategically placed on all 4 facades. Approximately 99% of the building experienced luminance levels exceeding 110 lux on a typical day. See? And importantly, the building incorporates glass with visible light transmission VLT of 42%, still keeping U value of windows, glasses to 1.6 watt per square meter Kelvin. You may not really capture these 1.6 watts per square meter, what it is. Actually, glasses are more conductive and radiant heat transmitters, very high components compared to walls. The heat transmittance, that is U value of a plain glass, is 6 watts per square meter Kelvin. But can you see, they have reduced it to 1.6 watt per square meter Kelvin. So they have not used normal glasses, but engineered glass. Also, solar heat gain coefficient is at 0.29, complying ASHRAE standards. ASHRAE standard, you can see here, ASHRAE standard for energy efficiency of buildings, that is ASHRAE 90.1. For climate zone 1, we'll discuss later, climate zone 1, maximum U value permitted for windows is 3.6. That means normal glass 6 watt per square meter Kelvin has to be dropped to 3.6. But you can understand this net zero building has dropped it further. That is how you reduce your energy to 50%. Water management. Rainwater from all roofs and non-roof structures is collected for use and groundwater recharge. You can groundwater recharge use. Treated grey water is used for landscape irrigation. Water efficient plumbing fixtures and flow regulators are used to reduce water consumption. Water metering is implemented to monitor continuous usage. Materials. Approximately 30% of the materials have recycled content. Now that will reduce embedded carbon. 75% of the wood utilized is either rapidly renewable or certified by the Forest Stewardship Council. 50% of the overall building materials are manufactured and sourced locally. So your transport costs down, that means embedded carbon goes down within 400 kilometer radius. Heating, ventilating, and air conditioning. The cooling load of the structure is 10,576 kilowatt hour per year. What they have used, a variable refrigerant flow system with R410A. But eventually they'll have to replace this 410A when scientists find new refrigerants. They are not harming the global warming, so they'll have to replace 410A. For the time being is okay. And the coefficient of performance of this refrigeration air conditioners, COP of refrigeration is 5.5 at 70% capacity, 100% capacity, 4 COP, that is compliant ASHRAE standard. Energy efficient and BEE 5-star rated fans and all the other equipment used are star labeled. Hot water needs are met using heat pump with an efficiency of 56% and COP of 3.6. The cold air generated by the water heating heat pump is utilized to cool the staircase area. Now that is being done in even in Sri Lanka. Now the heating by electricity is a crime. We can't use. If we use a heat pump, what is a heat pump? Heat pump is a refrigeration machine, but it as a main energy source to heat. It is the reverse cycle of a refrigeration machine. Heat pump is same, reverse cycle. But the important thing, refrigeration machine, if the refrigeration machine coefficient of performance, then the efficiency is 1. Heat pump is 2, always +1. So efficient. So we always use heat pumps for water heating. As a byproduct, we have cooled air. Now here they have used that for cooling staircases. ELV, the building incorporates energy efficient lighting fixtures and occupancy sensors. Home automation system is implemented. A lot of things. Featuring door and lock sensors, video intercom, it is various things. Smart building approach. The project has net metering, allowing for the seamless integration of renewable energy sources with the utility grid. See, additionally, a battery backup system with a capacity of 75 kilowatt installed. Now that ensures during night where there are no solar, energy is supplied to the building without using fossil fuel. So renewable energy sources of this building. Solar panels generating approximately 39 megawatt hours of renewable energy annually and are installed on the terrace. The system comprises of 62 solar panels, and I will give you the final figures. Annual energy consumption of the building is 37.2 megawatt hour per year. Okay, megawatt per hour year. Annual energy generation by renewable sources is 39 megawatts hour per year, higher than the usage. So it is net zero energy building. So this is not a myth, it can be done. Now, building services engineers' role, especially mechanical engineers, air conditioning engineers' role. Quickly we'll go through that. Reducing building energy consumption, that is by complying ASHRAE 90.1 standard. Using high efficiency equipment. Complying ASHRAE 90.1 when selecting HVAC equipment. Achieve operational carbon reduction, complying benchmarks. If it is a new building, reduce embodied carbon complying benchmarks. Reduce total energy use by 50%. Install renewable energy sources such as solar PV, wind energy, or geothermal energy, offsetting total energy demand of the building. Now that is the building services engineer's role. And also install solar PV storage devices such as batteries for use during nighttime. During nighttime. Building services engineers will go back here. So during nighttime, a normal solar PV system does not provide energy. So we need energy storage. Okay, we'll take very quickly reduction of embodied carbon. What we normally do, reuse building materials in renovation projects, usually save between 50 to 75% of embodied carbon. emissions compared to constructing a new building. Use low carbon concrete mixtures. Concrete can be the biggest source of embodied carbon for a new site. Utilizing fly ash in concrete could have achieved reduction in embodied carbon. That is aerated autoclaved concrete. We'll come to that. We'll come to that. Use of less carbon intensive materials for buildings such as rammed earth, soft wood timber, cross-laminated timber, stone, clay bricks, walls, like that. So these are how we use recycle, reuse building materials. Low carbon concretes, and these are much more energy efficient, called aerated autoclaved concrete. I personally, I think we have in Sri Lanka, we have done the first building utilizing aerated autoclave building is in Mathara, Anivilas. They are so good. Their thermal conductivity is so low. You don't really need air conditioners. What happens? These bricks have air bubbles inside. So lightweight, air bubbles inside means thermal conductivity is low. Simple as that. You can see in this table, thermal conductivity of brick 0.81, concrete 0.51, 0.12, 0.12 is AAC blocks. Now, during Anivilas in Mathara, we have to import these from Thailand. Fortunately, we do have AAC blocks in Sri Lanka. Manufacturing. The other material, low carbon thermal insulation. That is, this is a bio-based content. 80% content of product combines with hemp. Hemp, you may have heard hemp, with recycled jute bags. Hemp is a plant fast-growing biomaterial used for thermal insulation and wall paneling. And Sri Lanka, we have ICC. They produce this kind of a paneling. They call, now it is, I slipped the word. We have Sri Lanka, somewhat similar material. Use of carbon intensive material, that is like rammed earth. You can see rammed earth wall cladding. So finally, we use solar PV on roofs. But we need energy storage batteries. These are solar farm on ground level. So reducing carbon footprint, the methods, how do we do? How do we reduce 50% energy of a building? Quickly, we'll go through steps, actual steps. We'll have to find climate zone of your country, and that particular climate zone, ASHRAE standard gives you thermal values, like a wall, brick wall, what should be the U factor? Stone wall, what would be the U factor? A cement block, hollow block, what would be the maximum U value? Similarly, glasses, the most heat transferring element of a building, they give you the maximum U value that you should have. So we'll have to apply from ASHRAE standard. Next, minimizing ventilation load using ASHRAE standard 62.1. And verify the simulations for resultant RH. Now we do a simulation, and we can even find what would be the resultant RH in the building. ASHRAE standard has an upper limit. 60 RH is the upper limit of air conditioned space relative humidity. So we can see the simulation, what is the predicted value. If it is exceeding 60, it becomes 65, 70, we'll have to take measures. Minimize ventilation loads in higher occupancy buildings. We'll have to use demand control ventilation. Select equipment with minimum efficiency. Again, ASHRAE stand 90.1 we'll have to use. That is, when we select a chiller, when we select a commercial package unit, a VRV unit, we'll have to comply the energy efficiency limit. Either it is given in EER or COP or kilowatt per ton. Use of performance requirement for heat rejecting equipment like cooling towers. There are performance standard for cooling towers. You just can't buy because it is cheap. No. Fan power limitation, we'll have to use air handling units. Fan power limitations. We can't, for a given airflow, there's a horsepower limitation. That is all that. Minimum duct and pipe thermal insulation are values. All that has been verified and complied. Finally, use of energy control strategies using BMS. Now, what are the strategies? Most of these are coming from ASHRAE Green Guide. Unfortunately, in Sri Lanka, most of the building services, building management systems are just, showpiece. People just look at fans. Fans are working, chillers are working, temperature outside, inside given, that's all. No, there are energy saving strategies. These are the ASHRAE standards that we use for green buildings and net zero buildings. Building envelope heat reductions. First, we'll have to find our thermal zone. Now, Sri Lanka, we have 2 thermal zones. Unfortunately, in ASHRAE books, we have got only one, that is Katunayaka area. 0A. 0 means extremely hot. Katunayaka 0A is the climate zone. So if you know the climate zone, we can quickly ascertain the U factors for typical climate zone. Simply, we'll have to use these, we'll have to achieve these things while we are building the house or the building. That is all about. So understanding the U value, I think all engineers who are following this, you know all this. U factor is a rate of steady state heat flow through a building material, building component. Because you can't use thermal conductivity, that is Fourier's law, because this building envelope is built up of different materials, composite. It is a composite wall. So you'll have to use U factor. How to calculate U factor also I have shown here. You add the resistance of each layer. Total resistance, 1 upon total resistance is U factor. Now, for climate zone 0 for Sri Lanka, which is coming under climate zone 0, Singapore 0, India 0. So, U factors are given in this table. See, roofs. There are 3 types of roofs available. Insulation entirely above deck, that is a roof slab, concrete slab. U factor should be 0.22 or below. Metal building, zinc alum, 0.23 and below. Attic roofs, that is tiles, 0.153 or below. On the other side, you can see the thermal insulation R values. Walls, mass walls, 3.2, you don't need thermal insulation. Metal buildings, 0.53, steel frame, 0.3, like that. Floors, wall above grade walls, floors U 1.8, likewise. Now there's a little comparison for you to understand U values. In Sri Lankan normal buildings that we use, say concrete slab 150 millimeter, U value is 2.26. 2.26. If you want to convert this building to a green building or net zero building, you'll have to drop this to 0.22 with thermal insulation. Asbestos roof, normal asbestos roof, U value is 3 watt per square meter Kelvin. You'll have to drop it to 0.153. Zinc alum roofs, very hot, 5.88, but we use a glass wool 50 millimeters, so it is 0.83. But we'll have to drop it to 0.22. Brick walls, you don't need because that is very low compared to our standard requirement. Then we'll see another important thing of green buildings and net zero buildings. They use continuous air barrier. Unfortunately, in Sri Lanka, we don't use this. First time in Sri Lanka, to my knowledge, it was used in a building in Katunayaka, a innovation center, Star Garment Innovation Center. If you check the World Wide Web, you can see that is the world second building who won passive house rating. That is in Sri Lanka. I was proud to say that I did the air conditioning design, but not that. That is use continuous air barrier. In other countries where 4 seasons prevailing, like UK, every house, every building is checked for air leakage. That is called blow door test. They close all the windows and doors. Front door they remove. They install temporary flanges with a large axial flow fan and pressurize the entire building and see the delta P over a period. So that has to comply the standard. So leakage has to be minimal. What is here we talking about? A continuous barrier. See, you can see green color barrier right round. So that will give a continuous air barrier. So water vapor transfer is minimized. Right? Next is roof structures. Cool roofs. Cool roofs. Roofs has to be cool roofs. Roofs has to be heat reflective type, either silver color or white color. Metal roofs, if it is metal roofs, it has to be silver color or white color. Or zinc alum, you'll have to have light color roofs. I have one of the exhibitions. I told these manufacturers, why aren't you having light color? Why you have red color, green color? Rubbish. We need reflective roofs. So that those are cool roofs. Roof insulation, I'm not going to go through all these, but a roof insulation for an entirely above deck, we need insulation R25 for climate zone 0A. R25 is in inch pound. To achieve R25 insulation, we need 6.5 inches thick polystyrene insulation. 6.5, mind you, not 1 inch. You need about 6 inches. Do you really use insulation over the above deck? I don't think you don't. You don't. Not in Sri Lanka. But for a net zero building, you need minimum 6.5 thick polystyrene insulation. Similarly, a zinc alum, you need 2 types of insulation, R10 plus R19 fill cavity. So 2 R29 total value. So thickness would be 8 inches total, 3 inches plus 5 inches. When it comes to fenestration, glass, as I told you, normal glass has 6 watts. 6 watts per square meter Kelvin. This is the U value. Very high. But you got to drop it to 1.73 if you are doing a net zero building. You'll have to have double pane low E glasses. These are the engineered glass, the best. Low E double pane. The 2 panes, either nitrogen charge in between, and the outer glass interior surface is having a coating that reflects solar energy. Then permanent projections. Permanent projections also very much important in a house. There's a thing called projection factor. You will understand what it is. Projection factor is the awning width divided by the height of the window. The PF, the value of the PF, value of the PF rather, is increasing. What happens? Solar heat gain coefficient multiplier reducing. That means solar heat gain is reducing. So we'll have to have a larger fin here, a larger awning, probably with a fin as well, if possible, because that will cut the solar. In Sri Lanka, minimum 3 feet is required. Then a baseline building, as per ASHRAE 90.1, these are the air conditioners you must use for a building net zero. Package terminal air conditioners, package rooftop air conditioners, chill water system single zone, constant volume, and variable air volume. Let's see what it is. Residential buildings, we should use PTAC, package terminal air conditioner. Of course, we don't have in that particular unit here in Sri Lanka, probably split units with a higher EER. Remember, EER, that is energy efficiency ratio, should equal or greater than 11.3. 11.3. Unfortunately, Sri Lanka, whatever we bring it here, EER is 9 to 10. What is EER? Energy efficiency ratio. Simply EER equals cooling capacity in BTU per hour divided by power input in watts. Higher the EER, higher the efficiency. So when you select an air conditioner for your green building or a net zero building, you like to find 11.3 EER unit or higher unit for residences. For a public assembly buildings, that is 11,000 square meters and below. Those are like shops, small offices, classrooms, something like that. Better equipment is rooftop package units. People don't understand in Sri Lanka, this is the most efficient air conditioners available because these are factory tested, a fresh air entrance, exhaust, all inbuilt with the economizer. Night purge can be done. One single source, factory tested. You need to supply only power supply, condensate drain, and supply return ductwork. Now, same unit, horizontal delivery version, ducts supply and return ducts connected on the rooftop. Public assembly buildings larger than 11,000. That may be high-rise buildings, large commercial buildings. Preferred is chill water system, single zone, constant volume applications, air handling units, constant volume. Retail, that is 2 floors or fewer, shops, package air conditioners. So this is a rough idea about how to save energy when selecting a air conditioning chiller, which is the most energy consumed equipment in the entire building. ASHRAE 90.1 gives particular energy efficiencies. Now this is a water-cooled chillers, positive displacement type, like screw types, not centrifugal though, screw types, scroll type chillers or magnetic bearing chillers. That is no, that cannot be used because that is centrifugal. So screw chillers, 75 tons, 75 to 150, 150 to 300, 300 to 600. So I have just 150 to 300. Your efficiency should be kilowatt per ton, 0.66 kilowatt per ton at full load. Also, you'll have to check part load value, 0.540. It we call integrated part load value. Because chillers are not operating at full load all the time. Most of the time, chillers are operating in a building part load. So we'll have to check. No point we are purchasing a chiller, full load efficiency is great. When the chillers are operating part load efficiency should be higher. That is what is given here. I'm going to give you a little example, quick example. This is CEng Towers in Colombo. This was built 1994. I was instrumental for designing the system, initial design for tender, and subsequently it was improved. That is the story that I'm going to talk. I'm going to calculate carbon footprint and the carbon footprint reduction. Now, CEng Towers, I have calculated January 2012 to December, entire year, total power consumption, kilowatt hours, 4.5 million kilowatt hours. How to find the CO2 emission? We'll have to multiply this by a value, 5.835 into 10 to the power minus 4. This for our combination of coal power plant and a diesel power generators. So this is the value, 5.8. When you multiply this, the answer is GCGI emissions in metric tons carbon dioxide equivalent. So that what is that? That entire year, carbon dioxide emission, 2,645 metric tons we have emitted. That's the equivalent. Okay, right. So that is the normal carbon footprint of the building we call. But in 2015, we installed a very, very energy efficient magnetic bearing centrifugal chiller with a innovative building management system with energy saving strategies. Outcome was 2016, outcome was 4.5 million became 3.1 million kilowatt hours. Earlier, it was 2.6 2,645 carbon dioxide became 1,893. 31% reduction in carbon emission. This is green buildings. This is how we try to achieve carbon neutral also. So coming back to energy efficiency equipment, the energy efficiency ratio is given for single phase split units. Very, very very tight energy efficiency values are given. 12.1 for a 65,000 and below, these are latest. And large three-phase air conditioner with large condensing unit. So we have given the values. VRV values again given 11.2, 13. SCR is seasonal energy efficiency ratio. We don't take because that is for 4 seasons. We take EER 11.2 should be the level. Then the cooling towers, there's a value, minimum energy efficiency value. Let's see what it is. When we select a cooling tower, we have a flow rate. The performance index in the 90.1 is 40.2 GPM per horsepower. Now we'll have to find this. Cooling tower water flow rate, what we selected is 320 cubic meters per hour, converted 1,000. Performance value is 47.8. So it is above 40. So this is compliant. See, you can't just purchase cooling towers. At the same time, heat rejection equipment like a cooling towers also we'll have to find, and we'll have to control the fan speed if we are running the cooling tower for 24 hours. This has another energy cap, minimum efficiency requirement. Horsepower limitation. Say we have selected the air handling unit. The limitation is horsepower should be equal of actually 7.3, just there. Finally, use of building management systems reduce energy. Won't discuss these things, won't try to control these things. They are merely a gimmick. But you'll have to use these things to achieve green buildings, and more than that, achieve net zero buildings. We'll take one by one. Now, I will give you an example. I took this real-time picture on a sunny day, just about 2 o'clock. These Ceylon towers. But when you analyze, the chiller is loaded only 71%. How efficient is the building and the equipment are? Chill water reset. What is chill water reset? As you know, our chill water produced by the chiller is at 7 degrees C, leaving and incoming 12. Actually, it is 6.6 and 12.2, but say 712. But if you generate chill water at 7 degrees C throughout the day, it is an energy killing. Because part load, What is part load? Building part load. Building part load maybe in a day. If it is early morning, sometimes night, part load. Around 12 o'clock to 3 o'clock, maybe 4 o'clock, peak. Rest is part load. What we do, we raise the chill water temperature. Every chill water temperature rise 1 degree. It saves compressor power. Chiller power saving is 1 to 1.5%. Direct savings. But important thing is we should do this during part load. During part load. We can't use this during peak time. So what will happen? You can't bring the environment to comfort zone. Relative humidity will increase, condensation will occur. So high RH is not that what we require. So it is used only part load conditions. Now that is in ASHRAE standard 90.1. Chill water. Any chiller exceeding 88 kilowatts should have this function. Next one is fan cycling. Now fans are used, the fans are working continuous. Fans are working continuous full load. That is energy killing. Say when 100% working, when it is reduced at part loads, fan cycling. The fans used in car parks, fan cycling is used because during normal ventilation and we need higher amount of ventilation during a fire. Usually 6 air changes for normal ventilation, 10 air changes for during a fire. So you need a couple of fans to trigger during normal ventilation, but in a fire. Duty cycling. Duty cycling is to avoid setting unnecessary electrical demands, peaks caused by synchronized startups of equipment. It has to stagger. Optimum start-stop is a very important thing. Optimum start-stop, a strategy. We don't need to start the building 8 to 5. Optimum start-stop. Sometimes we can learn by learning the BMS behavior. You don't believe we can run chillers at early in the morning. Come on, 6 o'clock. What are you talking? 6 o'clock. You run the chillers. You cool the building. The chillers won't load maximum. But when you analyze a building running 8 to 5, air conditioning chiller running 8 to 5 for a complete day, all chillers are working more, let's say Monday to Tuesday, 7 o'clock we start the chillers. Thursday, Friday, normal 8 o'clock. But when you analyze total energy consumption per week is very much lower. That is also required by the 90.1. Next one is unoccupied ventilation night purge. We can have air handling units to run during night, maybe early morning when the air temperature is colder, 24 degrees, 22 degrees, run the air handling unit only to circulate air. Actually, you take 100% fresh air, blow through the building and exhaust. That will chill the building, that will reduce the energy consumption. Electrical demand limiting is a fantastic implementation of BMS. Demand limiting, when the demand is going up, a predetermined value, BMS trigger a signal to all the DDCs. Okay, send the signal to HU, set point increase 1 degree. So 24 degree becomes 25 degree, chiller will unload. So electrical demand limiting. So I think you have understood of these BMS strategies also. So these are some advices. Building should be designed firstly to significantly reduce energy consumption and then to meet remaining loads with the renewable sources. Achieve 50% energy saving of the building. Don't forget to use recycled low carbon materials to reduce embodied carbon, because net zero building needs that. Next one, reduce thermal loads, operational loads and carbon footprint of the building to reduce operational carbon. Use renewable energy sources and store energy for when renewable resources are reducing. During night, we need energy. So that is given by battery storages. Total energy consumption should be equal or decrease against the energy produced in the building. So renewable energy has to be produced in the same source. That is also a requirement for net zero energy buildings. So that is all about net zero energy building. That is not a myth. We can do it if we are really interesting. Okay, thank you very much for listening this. If you have any questions, we have the time. How to calculate the plant room efficiency? I have a couple of questions. So you can do that. To do that, kilowatt per ton, you'll have to find kilowatt per ton for air handling units, fan coil units, chillers, cooling towers, everything kilowatt per ton, and add. Usually, 1 kilowatt per ton is quite good, but now with this form of energy reduction, we are going 0.8 and even below. Some people are talking about 0.5. I will try and reply these answers without taking time, because we are a little late on the schedule. I hope our operators will record this and give me the questions. I will send you the answers. Next one, can we use carbon pricing scenarios? We not increase the efficiency of net zero carbon buildings if we can. How? Use carbon pricing? What do you mean? I will go through it and come back. Net zero energy building and net zero emission building are the same, just same concept. Can we consider carbon emissions and GHG emissions as the same? Yes. Well done. Yes, these are the yeah, there's a comment from Architect Jandapera, Chairman of Green Building Council as well. Thank you, sir. Right, okay. Hope this has some benefit to you.
Excuse me, sir.
Please save the yes.
So I'm Chintaka Vaidyaratne, and we have achieved the net zero carbon building in Sweden. There are some building net zero carbon building and the net zero carbon cities also at the moment. If anyone want to get more idea about can read the Paris Agreement or Doha or Kyoto portfolio, such as, so they are now they have improved up to that level.
Very good, very good, very good, very good. That thanks for contribution. And but I have seen, I have been to Denmark, and I have seen something. Yes, please.
It has done very recently, I think 6 months ago,
yeah,
like that,
yeah.
because it mentioned in the COP23.
Oh, right, fantastic. I have to mention something. You see, When you take places like Sweden, Denmark, Norway, they are very cold countries. I will give a little example. Where, during probably 1980s, I had this Grundfos magazine. They are explaining an air conditioning system of a bank building, 2-story. Total capacity is 2 tons. So I couldn't fathom what they are talking about. To see their temperature, outdoor temperature is 22. Indoor temperatures, they are slightly heating up, but you need still air conditioning. So all in all, those countries, the energy we are talking about are very little. So to mitigate also, that is somewhat easy, I presume. Then the places like where we live, these are a hot and humid climates. So for us, it is a great difficult task. Anyway, good. Thank you very much. Any suggestions? Any questions before we wind up? So thank you very much, and please remember, we'll have to safeguard our Earth. That means we'll have to limit our global warming as per the Paris Agreement, Kigali Agreement, to keep the global warming to 1.5 degree level. So whatever you do, your action must be to safeguard Earth, to reduce global warming. Thank you very much.
Okay, sir. Thank you very much, sir. Appreciate your expertise and time shared with us. Your insights made our debate truly enriching. Thank you for being our resource person, sir. Once again, thank you very much. As well as thank you all for being a great audience today. Stay tuned with our upcoming events. Good night. Stay safe, all of you. Thank you, sir.
Thank you very much.